I would like to start with explaining what is going on the blackboard. So this is my yesterday's lecture. Notations on top, main statement on the bottom, and I will cover this in 3 or 4 minutes. Now, on the left, on all these are notations. These notations which were already introduced on the top blackboard, this was not introduced yet. It would be introduced in today's lecture. This is just to keep notations on the blackboard so that if you, well, there are many. If you forget some, you can look at the blackboard and you normally would find the most important ones. So don't look at this blackboard for a while. And especially, please, do not try to guess what's that. It was not defined yet. It would be defined shortly. Now, what was told during yesterday's lecture? So we consider, so I prefer to stick to one concrete example, no multi-curves. Just consider one simple closed curve on a smooth surface. And suppose that this curve is non-separating. We cut the surface along this curve, like here. And we still have a connected surface with two boundary components. So let's take gamma like this. We can start applying diffeomorphisms of our surface to this curve, and we'll produce plenty of other curves. And we consider the entire orbit of the mapping class group of this curve. So we consider basically all possible non-separating simple closed curve on a smooth surface of genus G, no punctures, just smooth surface of genus G. And we consider them up to homotopy or up to isotopy. It's the same. Now, this is something which is purely topological. Now, let us introduce hyperbolic metric on our smooth surface. In the presence of a hyperbolic metric, all our simple closed curves get a unique geodesic representative. So every simple closed curve gets a unique geodesic representative in this particular metric. So it becomes a simple closed geodesic. And we measure length of this geodesics. And we want to count what is the number for a given hyperbolic surface x. What is the number of simple closed non-separating geodesics of length at most L. It is known that this number is finite. We want to get an estimate of this number, or to get as much information about this number as possible. Now, the trick is the following. Instead of considering the space of all possible hyperbolic metrics Mg, let us consider a cover of this space. And now we'll consider pairs, hyperbolic metric X, and distinguish some choice of particular simple closed non-separating geodesic alpha on our hyperbolic surface. So we have infinite cover because, of course, there's infinite number of simple closed non-separating geodesics on every hyperbolic surface. We get an infinite cover. However, if we'll impose this condition on the length of simple closed geodesic, we'll pick finite number of points out of the fiber of this cover, right? So this covering space is denoted mg gamma, and a point of this covering space is almost the same as the following thing. So first, I suggest to look at the picture. So a point of our covering space, a hyperbolic surface X, and a choice of some distinguished individual simple closed geodesic. Let's cut the surface along this simple closed geodesic. We'll get a hyperbolic surface with two boundary components of equal, two geodesic boundary components of equal length, L, where L is the hyperbolic length of our hyperbolic geodesic gamma in hyperbolic metric X. And by definition, this object is a point of the moduli space of surfaces of genus G-1, we killed one handle, with two boundary components, with boundary components of length L and L. The fact that we have 2 points here, it's a matter of convention. I did not specify that considering surfaces with boundary, traditionally one give names to boundary component. So we can say that this is boundary component number 1, and this is boundary component number 2, or vice versa. So basically, we have 2 ways to attribute numbers or names, like Jenny and Paul, whatever, to these boundary components. And that's why there are 2 points. OK, now 2 more notations. First, let us consider the characteristic, the function which is defined on positive real numbers with values in positive real numbers, which is just characteristic function of the interval from 0 to L. So f of x, where x is non-negative real number, is 1 when x is between 0 and L, and it is 0 when x is too large. By definition, our counting function, we want to count how many simple closed non-separating geodesics gamma of length at most L can we find on the hyperbolic surface x, and this counting function is denoted by Sx of L gamma. By definition, we can write this function as sum over the orbit of the mapping class group of gamma, and for each point of this orbit, we compute the length of the corresponding, so this orbit is homotopy classes of all possible simple closed non-separating curves on a topological surface. And then, in the presence of hyperbolic metric x, they become simple closed geodesics. We measure their length, and we evaluate our function f, characteristic function from 0 of the interval from 0 to L, on this length. If the hyperbolic geodesic alpha has length at most L, we take it, because f would be equal to 1. If the length is too large, we do not take it. The value of f would be 0. So do you agree that this counting function is just by definition this sum? So here I prefer to slow down for a second. This is important for me. Up to now, it was just notations. I was playing with notations. So it's sort of, so does everybody agree with this line, that this is the number of simple closed non-separating geodesics on x of length at most L? Right? Cool. Now, the main result of yesterday's lecture was the computation of the average number of simple closed non-separating geodesics of length at most L with average with respect to all possible hyperbolic metrics. So we take this function, and now we consider it as a function of x depending on parameters L and gamma. So gamma, actually here, you can forget gamma. Gamma just says that it's simple closed non-separating geodesic. Gamma here is just to follow notations of Mirza Hani, because she considers also multi-curves here. Forget about it. So L is parameter. Now the variable of function is x, will vary hyperbolic surface. So we'll evaluate the number of simple closed hyperbolic geodesics, non-separating hyperbolic geodesics on the surface x of length bounded by L. And then we'll take the integral of this function with respect to all possible hyperbolic metrics. So we'll compute this number in average. What is the average number of simple closed hyperbolic geodesics of length at most L in average for all possible hyperbolic metrics on surfaces of genus G without punctures? So this is the definition of the object which we are computing. And now comes the computation. First part is just a trick. This S of x by this formula, it's the sum with respect to the orbit of the mapping class group. And this orbit of the mapping class group is exactly the fiber of this cover. So to compute integral of this function of the moduli space is, so this function, to compute the integral of this sum with respect to this moduli space is the same as to compute the integral of this function with respect to this cover. Again, I prefer to slow down. Yes?
In the infinite cover, you consider pairs X and closed non-separating geodesics?
Yes.
Non-separating?
Yes. Simple closed non-separating geodesic. So function f is characteristic function, and it will pick only finite number of points of this out of this fiber, infinite fiber of our cover. So we'll have only finite number of terms here. So does everybody agree that this integral is the same as this one? So here we're integrating function, which is actually the sum of values of f with respect to all points of the cover. So it's sort of tautologically the same. So this equality is sort of tautology. Now, what is not tautological is this red equality. Because now I will use the following thing. So I will use the fact that this point, where is it? Yes, so the point x alpha of our cover is up to this coefficient 2, which is hidden in this 1/2, is the same as the point like this in the moduli space of bordered hyperbolic surfaces with hyperbolic boundary component, with two hyperbolic boundary components of the same length L. So since this object is the same as this object, so we have bijection, and integrating with respect to this cover is the same as integrating with respect to the following thing. So when we have a surface like this, how can we come back? So we have to, we know already, we fix the length L of the boundary hyperbolic boundary component. To reconstruct uniquely this surface, we have to indicate what is the value of twist parameter. Because when we'll glue two boundary components, we still have freedom of a twist, which we use to glue the boundary components. The twist parameter varies from 0 to L, and length of this geodesic and twist parameter make part of Fenhill-Nielsen coordinates. So I split it out two Fenhill-Nielsen coordinates out of all Fenhill-Nielsen coordinates, and I'm disintegrating. So we have to integrate with respect to all possible boarded hyperbolic surfaces like this, with all possible L's, where this small l varies from 0 to L capital, which is our bound for the length of geodesic. And also, we have to integrate with respect to, so this is integration with respect to the length of the boundary component. And also, we have to integrate with respect to all possible twist parameters, which vary from 0 to the length of the hyperbolic geodesic. And also, we have to integrate with respect to all possible boarded hyperbolic surfaces in this space. Again, I prefer to, now let me just shut up for 30 seconds and look at this equality. Just stare at this equality and try to convince yourself that I'm not cheating. I have nothing to tell more. I have nothing to tell more. Just look at it for 30 seconds, then I will try to answer to your question. So look at this equality for 30 seconds. And also at this picture. I'm ready to answer your question. Well, probably not ready, but
Can you explain the 1/2? Why?
Oh, yeah, of course. This is a matter of a pure conventional matter, because in definition of this space of boarded hyperbolic surfaces with two boundary components, Mirza Hani uses the convention where every boundary component has a name. It's attributed the name. So when we have a surface like this, you do not know what side of your geodesic is Jenny and who is Paul. You can choose, there are two choices.
The fact that you can split the measure in dl, d tau, dy is because the Weil-Peterson
is defined by in terms of Fenchel-Nielsen coordinates, yes.
okay, and so it splits as
And this is, and we chopped out exactly a pair of dual Fenchel-Nielsen coordinate, length of a geodesic and twist along this geodesic. Yes?
That's because you seem to count unoriented geodesic.
Yes.
It's oriented.
Yes, yeah. And, yes. Okay, if you are convinced in this equality, then we are done. Because when we integrate with respect to the twist parameter, we just get L. So we have to an integral from 0 to L of this integral is by definition the Mirza Hani Weil-Peterson volume of this moduli space of boarded hyperbolic surfaces with two boundary components of length L. So this is this integral. Integral with respect to d tau is just L. And the last integral remains. I cannot do anything with this. But we reduced our computation of average number of simple closed non-separating geodesics to integral from 0 to L of Mirza Hani Weil-Peterson volume of this moduli space times L. Now, as a black box, I ask you to believe me, and this is another work of Mirza Hani, who proved that this volume is polynomial in L of degree 6g minus 8. So we multiply it by L, we get degree 6g minus 7, and we integrate with respect to L, we'll get one more degree, so we'll get, as this quantity becomes a polynomial in L of degree 6g minus 6. So I do not care about lower terms. I'm very much interested in this coefficient C gamma. We'll use it. But we already proved that in average, the number of simple closed hyperbolic geodesics is a polynomial of length bounded by L, sorry, non-separating, is polynomial in L of degree 6g minus 6, which is a very nice result. We used as a black box this information that the volume of Weil-Peterson volume of the moduli space of boarded hyperbolic surfaces is a polynomial, but at least I hope that it is not completely astonishing. We have seen a couple of polynomials like this at the lecture. Okay, now only in 20 minutes, I already told everything which was told yesterday in an hour, and now I still have 40 minutes to tell something else. And I need to introduce one more actor. I need to introduce the space of multi-curves. And so this section is just a recollection of results of Bill Thurston, who, with his incredible imagination, realized that all possible simple, well, homotopy classes of simple closed curves can have very nice structure and can be organized and placed as sort of integer points of some nice topological space. So I'm following example which is treated in chapter 15 of the book of Farb and Margalit, a primer on mapping class group. So you can find all details in this book. So this chapter, to my mind, is a marvel. So it suggests, well, it treats simple closed curves on 4-punctured sphere, and it suggests how to describe all of them, how to encode them, how to parameterize them, and how to organize them into a nice space. So you agree that 4-punctured sphere is basically the same thing as 3-punctured plane. we can consider stereographic projection of four-punctured sphere, putting the north pole at one of the punctures, and then we unwrap the rest to a plane with three punctures. Now, we're considering non-peripheral curves on four-punctured sphere, so we are not allowed to consider simple closed curves, as always. We are not allowed to consider a curve which goes all around these 3 points. It would be peripheral. It would contract to infinity, to a north pole. And the suggestion of encoding simple closed curves like this is to encode them using train tracks. And I apologize, there are experts in the room who know much more than me about train tracks, but I need them. So the suggestion is the following. Suppose you have a simple closed curve like this. The suggestion is to start progressively, you see, deforming it to something which you see on the right picture. And we want to encode. So I can progressively deform it to this guy. And to be able to reconstruct the original simple closed curve, I have to note how many strands of my simple closed curve go at each place. So here, I have only one strand, right? I put weight 1. Here I have 2 strands. I put weight 2. Here I have 3 strands. I put weight 3. And what we get is a very special graph, which is called a train track. So it's a smooth graph, smoothly embedded into our surface. And the vertices of this graph also have smooth structure. So we have well-defined tangent line at every vertex. And they are sort of just the word train track is self-explaining. I think that I wouldn't give a formal definition of the train track. You can guess what it means. And also, we consider this graph with weights. And there is a rule for the weights. It's like, well, coming from this origin with strands. Your strands cannot appear from nowhere and cannot disappear. If there are 2 strands coming into a vertex, then they would continue. There would be 2 strands continuing. So here, for example, let's take this vertex. We have weight 1 here, weight 1 here. So, and the tangency is like this. So we'll continue with weight 2. Here we have weight 2 on each side. So we'll continue with weight 4. Now here we have weight 4. Here weight 2. Here weight 4. So we'll continue with weight 6. And this 6 perfectly matches these 3. We have 3 coming from here and 3 coming from here. So at every switch, there is a balance between sort of incoming flow and outcoming flow. OK. Here's the definition of the train track. So the suggestion is to encode simple closed curves by weighted train tracks. And now the nice thing about this story, which is specific for four-punctured sphere, is that the encoding is particularly simple. Now, as an exercise, I suggest to consider the following 3 train tracks and to decide whether they might carry a simple closed hyperbolic geodesic and indicate legitimate weights if they can. And if there are plenty of solutions, if the solution is not unique, it would be nice to describe the entire family. So it's just an exercise on train tracks. Say, is this train track legitimate to your mind? Oh, I see that some people are dubious. I agree. I don't really like it. Because if you open it up, just consider a curve like this. So it goes all around this point, right? It encircles 3 points out of 4, so the complement encircles just this point. It would be peripheral. So one has to be minimum careful with train tracks.
What's the problem here?
Huh?
What's the problem in the second count that you change?
Here, we do not want to consider, sorry, with train tracks, of course, there is no problem. But this train track cannot carry a hyperbolic geodesic, because if you sort of go back from a train track to a simple closed curve, you will get a simple closed curve which goes all around a single point. In hyperbolic metric, it would be a curve going around a single cusp. So it's not essential. It would shrink to a cusp.
Cannot this one have just, if you just split in the section, like where they kind of join?
Yeah, that's exactly what I'm suggesting. I will put my finger here and I will split it.
This does not give a geodesic.
It would give a curve which goes all around this point. And this is the trouble. Yes?
How do we know that every train track can give back to a curve uniquely? I mean, I don't know how to do that procedure.
About uniquely, I never claimed this.
Okay, so how do I get one?
Well, we'll arrive. Well, first, I cannot give a mini course on train tracks in 7.5 minutes. But still, I will try to convince you that in this particular example, things are not bad. So first, I claim that, following Farb and Margalit, I claim that any simple closed curve on a 4-punctured sphere can be encoded by one of the 4 basic train tracks. I'm not saying uniquely. We'll see what is the source of non-uniqueness. So first, you agree that up to isotopy, since we do not consider peripheral curves, any simple closed curve in S04 can be drawn inside the 3 squares like this. Right, I contracted a little bit. OK. Then, by further isotopy, we eliminate bigons. So here we have bigons of intersection with vertical lines. So I don't like this bigon. I will contract my curve a little bit, and hop, bigon disappeared. So you agree that I can eliminate bigons, right? Stupid bigons. OK. Now, each connected component of the intersection of our simple closed curve gamma with a corresponding square is now of one of these 6 types presented at the blackboard. Right? I'm a little bit fast, but you can convince yourself, looking at the left picture, that every piece of our curve is represented by one of these patterns. Now, gamma is essential. So it cannot use both types of horizontal segments, right? If we have this horizontal segment and this horizontal segment, then at some point we'll have the topmost horizontal segment like this, the bottommost horizontal segment like this, and we'll have the stadium, and we'll get peripheral curve. No way. So there are restrictions. And also, it cannot use an arc like this and an arc like this simultaneously because they are intersecting. So there are 2 restrictions. One cannot have this guy and this guy, this guy and this guy simultaneously, and this guy and this guy simultaneously. So if you draw all possible ways to place this together, then you will see that the resulting curve can be deformed to one of these 4 train tracks. I agree that I'm speeding up. It is actually, it's very simple, but it is very simple when you go not with the speed of a jet, but with normal speed. You have to look at this picture for a couple of minutes. And at the beginning, you do not believe. And after 2 minutes, it becomes obvious. So, and this is the only way to proceed. The book of Farb and Margalit is fortunately accessible online. Just type the name of the book, and you can look at the chapter 15, and there are all the details, and you can find many more interesting things. But I gave sort of a sketch of an idea why every simple closed curve on four-function sphere can be carried by one of these four train tracks. So let's organize them in a space. So for every train track, it is sufficient to indicate, for example, let's consider this one. It's sufficient to indicate weight x on this edge and weight y on this edge to reconstruct all the weights. Because this x is split into x over 2 and x over 2 here, y divided by 2, y divided by 2 here. Here we have x plus y, and here x plus y over 2, x plus y over 2, right? So these two coordinates define everything. And also, if you choose any pair of non-negative even integer numbers x and y, you see clearly how to find a simple closed curve carried by such a train track, right? OK, so the points, the even points of each quadrant represent simple closed curves. Now, let's consider formal objects allowing to x and to y be any non-negative real number, just to cover the entire quadrant. And now also I would like to glue together the sides of the quadrants in the following way. So what if one of these x or y is equal to 0? For example, what does it mean that the weight here on this strand is equal to 0? It means that nothing goes here. Basically, and nothing goes here. We can erase it. Oops. So when this coordinate is equal to 0, we get a train track like this on the left and a train track like this on the right. And they correspond to this, so to points of our vertical line on this quadrant and points of this vertical line on this quadrant. We can identify them together, right? Similarly, if we have 0 here and 0 here, we can erase this piece and erase this piece, and we see that we get same train track, right? We can deform the train track. So we can glue this side with this side. So gluing all together, we get nice space homeomorphic to R2. And the integral points of this nice space, of this R2, correspond to isotopy classes of multi-curves in S04. So again, I know that I'm already a little bit late, but let me make a pathetic silence. It's beautiful, right? We started with some mass with some crazy curves wrapping around a four-punctured sphere, and whoop. You read the paper of Thurston, and he sees such a beautiful structure in this space. And the beautiful structure is piecewise linear structure plus integer points in this piecewise linear structure. And you can imagine that nothing is special about S04. You can do, it would be slightly more complicated or much more complicated for other spaces, and you will have to consider more train tracks, and there would be some polyhedral cone, but we'll still get piecewise linear structure, and we'll still have integer points. And actually, if you introduce, up to now, at any point I used hyperbolic metric. If you will use hyperbolic metric, all these integer points would become simple closed geodesics, or simple closed geodesic multicurves more generally. And actually, even non-integer points, other points, have a very nice geometric meaning. They're measured laminations, geodesic measured laminations. OK, but we do not need other points. I need only integer points, integral points. So, and I wouldn't speak about geometry of geodesic measured lamination. OK, so let's see what is going on. So similar considerations apply to any smooth surface lead to analogous space of measured laminations MLGN. It is endowed with a piecewise linear structure. And up to now, we didn't use hyperbolic metric. In the presence of hyperbolic metric, they have interpretation of measured geodesic laminations. And the integer points become hyperbolic multicurves. And also recall that in the presence of hyperbolic metric, we can measure the length of multicurves. So the hyperbolic length of a simple closed geodesic gamma in the presence of x, it's, well, the length of it, the length which we attribute to a multicurve, which is a formal linear combination of distinct non-simple closed geodesics which don't have pairwise intersections taken with, say, integer coefficients a, is sum of length of individual components taken with these coefficients a. Actually, this length function can be extended by homogeneity and continuity to the length function on entire ML. In our concrete example, it was R2. And by construction, it's homogeneous. Our length function is homogeneous. So what I need from ML is that it has piecewise linear structure. It has integer points. And in the presence of any hyperbolic metric, we get a very special length function, which is homogeneous. OK, now I forget temporarily the hyperbolic metric. And I want to define measure on my space. Well, train track charts define piecewise linear structure on which I insist during the last 5 minutes. And we also have an integral lattice in this space MLGN, which comes from integral multicurves. So as soon as, imagine that you have a vector space. In a vector space, you have distinguished volume element, but not one. You have an entire family of distinguished volume elements which differ by multiplication by constant. As soon as you have a lattice in your vector space, you have one particular distinguished volume element. You just normalize the fundamental domain of your lattice to have volume 1. So as soon as you have some space which is endowed with piecewise linear structure and with something which resembles a lattice, you have a distinguished volume element in this space. I should say that this claim is extremely naive. It took me 20 years to realize it. And this is what we use actually for flat surfaces, for moduli spaces of abelian differentials with square tile surfaces defining a lattice and so on. So surprisingly, the structure is not that rare in this story. Yes?
Sorry, could you please have a quick recap? I mean, I followed the last 5 minutes, but I didn't get what's the linear structure you mentioned, piecewise linear structure you mentioned.
So when we constructed, so for punctured sphere, so we had 4 basic train tracks representing sort of coordinate charts. And for each basic train track, when you choose as weights, you choose even integer numbers, such train tracks correspond to true simple closed curves, right?
Okay.
So this is the lattice.
But how is it really piecewise linear?
Well, I wanted to, well, in the case of 4-punctured spheres, you agree that there is piecewise linear structure.
I didn't agree.
Why? What worries you? The word piecewise or the word linear?
I didn't find anything linear from what you said. I didn't.
Do you agree that R2 is a linear space?
Oh, okay, okay.
Good.
Okay.
Okay. And now, one more remark. When you apply diffeomorphisms to your surface, simple closed curves and simple closed multicurves are sent to simple closed multicurves. So we have induced action of mapping class group on this space, which preserves our lattice, because our lattice has geometric origin. And that means that it preserves the volume element which we just constructed, which is already very nice. And what is even better is this theorem of Howard-Mazur, that the action of mod Gn on the space of measured laminations is ergodic with respect to the Lebesgue measure class. So any measurable subset of MLGn invariant under mapping class group has either measure 0 or its complement has measure 0. And any measure which is invariant under the action of mapping class group in the Lebesgue measure class is just Thurston measure rescaled by some constant factor. Okay, we'll use this theorem. So it's in all these stories, there is geometry, 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 geometry. Then, Ilya, one moment when you use version of Ratner's theorem or some ergodic theorem, and then again, geometry, geometry, geometry. But it's absolutely necessary, these kind of things. Okay, now let us discuss how do we count the measure of a set. So at least when I made my studies in elementary school, I was told that I have to put a square grid on my set and count the number of lattice points in the grid, and this gives the approximate value of the area of the set. And if you want to get better result, you make this grid smaller and smaller and smaller and smaller, and every time you count and you normalize, and at some point, and you compute the limit of cardinality of your set U, which you do not move, and with the number of points in a lattice with a grid of step epsilon, and you normalize it by the appropriate power of the grid, which is the dimension of your space, and you get the measure of your set. There is equivalent way. Instead of rescaling our lattice, we can just apply homothency, and we can either, so in this approach, I fixed my set and I move the lattice, or I can fix the lattice and I rescale proportionally my set, right? It's the same. It's exactly the same. These two quantities are the same. Just there is the cardinality of this set and of this set are the same because one is obtained from the other by homothency. Just I'm rescaling this picture by a factor 1 over epsilon, and then my lattice would become unit lattice, but the set would become much larger. Okay, so now I have to make a remark on what do I mean by lattice. You can use square lattice like here, but also the red points which are on this picture also can be used as a lattice. It is not lattice in the sense of something invariant by translations. It should be just some subset which has non-zero density in Zn. For example, the best, to my mind, the most expressive example of what subset of integer points can be used as a lattice for this counting, for counting the measure, is the set of coprime integral points in Z2. It is known that if you take a large ball and you compute, well, if you compute all integer points, you will obtain approximately PL squared integer points. But if you will compute only coprime points, which get to this large ball, you will get 1 over Z2 of 2 of PL squared. Now, note that the set of coprime points is actually quite a wide set. If you go far away, you can find enormous holes in this set, very large holes. But it can be used to compute the area of a figure in our plane perfectly well, exactly in the same way as we did for true integer lattice. Because when you rescale everything sufficiently well, then after averaging, everything goes perfectly well. I'm claiming that the measure which you would, so we can construct Lebesgue measure by putting atomic masses at all integer points and then applying this rescaling procedure and so on. What I'm saying is that you can put atomic masses at the coprime points and apply this rescaling procedure and so on. And what you get is our previous Lebesgue measure times this factor. That's all what I'm saying. And the reason why this set of sort of philosophical reason why one should expect that the subset of coprime points is supposed to have nice density. It's SL2Z invariant, right? So there is hidden ergodic theorem here. Now, I'm coming back to now Mirza Hani measure on ML. We discussed the Thurston measure. And the Thurston measure was defined like this. So we had some figure in the space in our space ML, which has piecewise linear structure. And we counted the number of integer points inside this figure. And then following the procedure which was suggested, we can start rescaling this figure and making it larger and larger. And then we count the number of integer points, we normalize, we get the Thurston measure. Now, Mirza Hani suggested the following thing. Let us, instead of taking all integer points, let's consider sort of a sublattice, which is sort of analogous to sublattice of coprime points in R2. What is this sublattice? It's just there you fix some particular integral multicurve, for example, simple closed non-separating curve. Take it as an example. You apply mapping class group, so you take the orbit of some integer points of fixed topological type under the action of the mapping class group, and you will get some weird subset which is schematically represented by these red points. And the claim is that it would produce a measure which is proportional to their Thurston measure. And the reason, speaking a little bit ahead, is that an orbit like this, the subset like this, is invariant under the mapping class group. And then it is corollary of ergodic theorem, of Mazur's ergodic theorem. OK, so this is the definition of Mirza Hani's measure. Instead of counting all integer points, we're counting only integer points from this subset. OK.
Okay, for the imbalance, but why the measure is non-zero?
Absolutely legitimate question. We'll come to it shortly. You're absolutely right. Why the density is, it's not obvious at all why the density is non-zero. If you take something like this, some subset which is not smart enough, usually you will get zero measure. I absolutely agree. We'll we'll arrive to this, and actually, this is a hint why the measure is non-zero. Well, but we're arriving at it, and so don't be frightened. There are many pictures, and we're almost there. So, to formalize, the Thurston measure of a subset U in the space ML is defined as follows. So we take all integer points in ML, and we scale our subset U with a large factor T. We compute the cardinality, the number of integer points, in U rescaled by factor of T. We normalize it by T power dimension of the space, and this is the definition of Thurston measure. The definition of Mirza Hani measure is very similar. You take the same set U rescaled by a factor T, but now you intersect it not with all integer points, but only with the points which live in the orbit of gamma under the mapping class group, which is subset of all integer points in ML. So clearly, the resulting measure belongs to the same Lebesgue, well, belongs to the Lebesgue measure class because we're taking only subset of set before. So the measure of any set can become only smaller. By construction, it is mod Gn invariant, and ergodicity of Thurston's measure implies that the two measures are proportional with some coefficient k, and we have to prove that this coefficient is non-zero. But the fact that they are proportional is these three lines. Now we can prove the main result. So,
there's a question.
yes?
Is the k gamma, is it related to the C?
Absolutely.
In some sense?
Yes, it is in very, very concrete sense. It is the same. We'll see it.
Okay, and the dimension of space of measured dimensions, why isn't it 6g minus 7 plus 2n? You said last time that
I don't know how to reply to this question. And I strongly prefer to, since I'm a little bit out of time, I strongly prefer to discuss dimensional questions after the lecture. Okay, so recall that we have length function, which was already defined. This is just reminder of definition of length function. So following Thurston and Mirza Hani, for each hyperbolic metric x, let us consider a unit ball in the space ML Gm. Namely, we consider all measured laminations which have length at most 1, measured in terms of the length function corresponding to hyperbolic metric x. So every hyperbolic metric x defines its own strange unit ball in the space ML. We change metric x, this space changes the shape. This unit ball changes the shape. Now, so we have individual unit ball for any metric, and we can measure its Thurston's measure, and by definition, this is just particular case of an abstract subset U. Its cardinality of the Thurston measure of unit ball is defined as follows. So instead of unit ball, we consider rescaled unit ball, but know that rescaled unit ball is a ball of radius L. So here we have a nice coincidence. It's not just rescaled set. It has geometric meaning. It's the subset of points where the length function has length at most L. Good. So this is our rescaled unit ball, and we intersect it with integer measured laminations. We divide by L power this power dimension of the space, and we pass to the limit. This is the definition of Thurston's measure. So we're doing this. Now, if we take another metric, we'll get another unit ball, and we'll do the same thing. And also, we have all these integer points, but also we have red points which correspond to some specific orbit of some individual multi-curve, for example, simple closed curve. And we can compute measures, Mirza Hani's measures of unit balls. Mirza Hani measure corresponds to counting only the number of red points which get inside of this ball of radius L and rescaling. So now I arrive to the summary of notation, which is on the blackboard. This slide is exactly these two blackboards. So X is hyperbolic surface. Sx of L gamma is the number of geodesic multicurves on hyperbolic surface X, where we fix topological type of multicurve, for example, simple closed non-separating curve, and we impose the bound for the length. Now, this is the average number of multicurves of topological type gamma and of length L with respect to all possible hyperbolic surfaces X. And we have seen in this calculation that this is a polynomial in L, which depends on gamma's parameter. And this is a polynomial of degree 6g minus 6 plus 2n. And C of gamma denotes the coefficient, this coefficient in front of the term of top degree. Now, we define a unit ball in the space of measured laminations, unit ball in terms of, defined in terms of individual hyperbolic metric X. When we change hyperbolic metric X, we change to this subset. So it's defined by means of the length function Lx. And this is the Thurston measure of unit ball. It's the number of points, not in unit ball, but in ball of radius L, intersected with integer measured laminations. And this is the Mirza Hani measure of unit ball. It's almost the same thing, except that we take the ball of radius L and intersect not with all integer points, but only with integer points which belong to the orbit of gamma. OK, and now this is the reminder of the statement of the main result. So the theorem of Mirza Hani says that this counting function Sx of L gamma, so X is our concrete individual hyperbolic surface, L is bound for the length, gamma is topological type of multicurve, is expressed in the following way. Now I can disclose all ingredients. The dependence on hyperbolic metric is hidden only in this factor, and this is the Thurston measure of unit ball. There is neither L nor gamma in this factor. And X appears on the right-hand side only in this factor. Now it is multiplied by C of gamma, which depends only on gamma, and this is our coefficient in the averaging counting function, coefficient of the top term of our polynomial. So it depends only on topological type gamma. And there is a denominator BGN, and BGN is just the average value of all possible Thurston's measures of all possible unit balls with respect to all hyperbolic metrics. So this BGN is just the average of this thing. And this was the main result which I wanted to discuss, and now I'm ready to prove it. So this slide is the proof. So I repeat probably fifth or sixth time the notations, but basically the proof is playing with notations and only one non-trivial, well, slightly non-trivial passage. Now everything is completely prepared. So this is our counting function. We want to prove something about this counting function. It's the number of simple closed geodesic multicurves of topological type gamma and of hyperbolic length at most L. And now we'll apply definition of Mirza Hani's measure mu gamma to the unit ball Bx associated to this particular hyperbolic metric X. And also we'll use proportionality of Thurston's measure and Mirza Hani's measure with some coefficient k gamma. We get the following. So now I'm not averaging anymore. I'm considering this individual Sx of L gamma. I divide it by the power of L which appeared in our averaging result. So we know that if we average this quantity, we get polynomial of this degree. So I'm dividing by their term, which corresponds to the top degree of polynomial in L. And I'm computing the limit. By definition, this quantity, numerator, is the cardinality of rescaled unit ball in metric X, rescaled by factor L, which is the ball of radius L, meaning that this is the set of all possible measured laminations, measured geodesic laminations for which the length function is at most L. Not only integer points, all of them. And this is the orbit. So this is a discrete set. This is a subset of sort of integer points, which is the orbit of mapping class group of our particular multi-curve gamma. So this intersection is exactly all possible multi-curves of topological type gamma and of such that the length function evaluated for them has value at most L. So this numerator is just definition of this quantity. So nothing happens here. Now this is, by definition, we pass to the limit. By definition, this is Mirza Hani's volume of unit ball. We've seen it. Mirza Hani's measure of unit ball is proportional to Thurstons' measure of unit ball with coefficient k gamma. We still do not have control of this coefficient. It might be 0. But we know that they are proportional. And basically, we have to now to compute the scaling factor. So how can we compute the scaling factor? K gamma. So recall that BGN is average of Thurstons' measure of unit ball with respect to MGN. So if we integrate only this quantity, we get MGN. If we multiply it by K gamma, we'll get K gamma times BGN. Yes?
K gamma is independent of X.
That was because both in definition of Thurstons' measure and Mirza Hani's measure, hyperbolic metric is non-present. It was defined topologically. We were counting integer points. And the observation was, the fact that two measures are proportional was due to the fact that both measures are invariant under the mapping class group, and that Masur proved that Thurston measure is ergodic with respect to the action of mapping class group, meaning that any measure which is invariant under the mapping class group and which lives in the same Lebesgue class should be proportional. The only thing which we didn't prove is that, and in Mirza Hani's measure is forced to be in the same Lebesgue class because we're counting only part of integer points, not all of them. So Thurston's measure clearly dominates Mirza Hani's measure by definition. So the only thing which we have to prove is to prove that this density K, this K gamma is non-zero, but the fact that this is constant, it's the sort of two-step corollary of, it's corollary of two facts, that both measures are invariant under the mapping class group and that Mirza Hani's measure is dominated by Thurston's measure and that Thurston's measure is ergodic with respect to the action of the mapping class group. So that this is, I agree that it becomes, sorry?
It's the theorem of Mary showed the K gamma equals. Mary actually showed that there was a lower bound for non-percent for the J.
This I didn't know.
Yeah.
But if you don't mind, may I just finish with this slide? I absolutely agree that this is very important, that K gamma does not depend on anything. But it is just the corollary of ergodicity. That all the...
You have to have something like the ball Bx is inside the ball, some constant ball X prime.
The balls are the same. The lattice, so it is... So the Thurston measure is in our analogy is equivalent as counting all integer points in R2.
No, but for example, if for some matrix the ball was just a segment and not a ball, it gives something different. Very, very, very similar.
Well, let me make a calculation. I think it would answer both questions. Because in this calculation, we'll first see that the integral is non-zero, and that actually we have computed it already. So this definition of BGN is integral of the Thurstons measure of unit ball. Up to now, I didn't claim that it is strictly positive. Well, but no, I can. At least for some metrics, it's really nice. So it is positive. So now, this is just formal passage. But we know that Thurston's measure and Mirza Hani's measure are proportional with this coefficient k gamma. So what is placed here is just Mirza Hani's measure. So we're integrating Mirza Hani's measure of unit balls with respect to MGN. Now, by definition, this Mirza Hani's measure is this object. We're taking a ball of radius L. We're intersecting it with the orbit of the mapping class group of gamma. We're normalizing, passing to the limit. That's definition. Now, by definition, this thing is Sx L gamma. We have seen it. So this is this line. Now comes the only non-trivial. So passing from here to here, I'm just using definition of Sx. Now passing from here to here, I'm using the following. I can interchange the integral and the limit because Mirza Hani proved that this ratio depend on L anymore, and F is integrable over the entire moduli space. This is a separate important exercise which justifies that we can interchange integration and passing to the limit. It requires justification. It was done by Mirza Hani. Now, if we're really allowed to interchange this, then what we get here is this integral is by definition our P of L gamma. And we know that it's polynomial of this degree in L, and that the ratio, well, if we divide this polynomial by L power top degree, what we get as a limit is coefficient in front of this top degree. So actually, we see that k gamma times BGN is C gamma. And in particular, we see that k gamma is non-zero. OK. So actually, we have finished the proof. Everything is computed. So you can look at the statement. We proved it. We proved this statement, and the very last thing is, well, this BGN is average. Two remarks. The BGN is the average of Thurston's measure of unit ball, where the average is taken with respect to all hyperbolic metrics. And there is a hidden theorem of Mirza Hani, hidden because you have to glue two theorems from two different papers. But she says it absolutely explicitly. So for flat surfaces community, it might be interesting to realize that this quantity BGN is, two things. First, this quantity BGN admits explicit expression as a weighted sum of all C gammas over a finite collection of all topological types of multicurves. You would ask me, come on, there, infinite number of multicurves because you are considering them with weights. Absolutely. But you can consider primitive multicurves where all the weights are ones. And there is only finite number of primitive multicurves. And then when you consider the same, so if you take a primitive multicurves and start changing weights, then when you sum with respect to all possible weights, you just have to multiply the result which corresponding to the initial primitive multicurve by product of zeta values at even integer numbers which correspond to some powers. So it is a very explicit procedure how to sum with respect to all possible multicurves when you know the answer for individual primitive multiple. Now, the second remark is that, and this was, sorry, I somehow rushed too much, this BG, if n is equal to 0, is nothing but Masur-Veech volume of the principal stratum of holomorphic quadratic differentials in genus G. And it took me many years to realize this, and it is explicitly written in the papers of Maryam. And one can generalize it slightly. I think that she probably didn't bother to do it. But BGN is Masur-Veech volume of the stratum where you have this number of simple zeros and this number of simple poles. And the very last slide, and this is really the very last slide for today, is that the Weil-Peterson volume of the moduli space of bounded hyperbolic surfaces, which we need to compute our coefficient C gamma, is actually expressible in terms of intersection numbers and in a very explicit way. And here are just two examples for M11 and for M12. So these volume polynomials which I showed you yesterday actually can be computed using intersection numbers. And this is the tie and the bridge to Mirza Hani's proof of Witten's conjecture about relations between these intersection numbers. But I'm already out of time, so I prefer just to leave it on the slide. Thank you very much. Sorry for being late.